Hello, this is the final part of the 2023 Oxford PAT. We've got 3 questions to go. We're up here on question 24. A ship floating at anchor moves vertically only as waves on the surface of the sea cause the surface height to vary with position x and time t as that. Right, so we've got one of these usual wave functions going on here. So just to go through this one more time, I know I've mentioned this before in previous videos, so we don't necessarily need this to answer it, but let's just see what all these bits are that are going on here. So say, let's ignore the VT bit for the moment. So say you just started off with a sine wave. So you've got that sort of thing going on, and it's going to be crossing the x-axis every pi. So we're going to have pi, 2 pi, 3 pi as we're going along. So we've got 2 little transformations here. We've got the 2 pi over lambda bit is rescaling the x-axis essentially. I mean, you can think of what we often say at A level as being this, this stretch of 1 over A in the x direction as being a rescaling of the axis. You're just changing what the numbers are. So that is changing it, is dividing this pi, 2 pi, 3 pi bit, all these numbers we've got here, is dividing it by the 2 pi over lambda. So what we end up with is we've still got our sine wave looking much the same, but these points are now lambda over 2, lambda, 3 lambda over 2. So we're turning the x-axis into the language of wavelength here. So you can see now, once we've completed one oscillation, we've got to wavelength. So that's why you see this 2 pi over lambda crop up quite often. So just to change it to be the wavelength of the wave. Then we've got this A at the start here, which is just stretching in the y direction to get our amplitude up to whatever it will be. So now we're talking about amplitudes and wavelengths on our waveform that we've got. Then when they add in the minus VT, we're just getting a time variant shift. So we're translating the wave in the x direction as a function of time. So we're just setting it in motion really and saying, right, well, let's set this wave off to the right and we'll just have it moving as a function of time. So that's everything that's happening here, just to understand what these look like. So when they ask us what is the period P of the ship's vertical oscillations, it's saying, well, how long does it take it to complete a wavelength? Well, if it's moving at velocity v, which we're getting from here, and it's got to go through a distance lambda in order to complete a wavelength, then the period that we're going to have is going to complete one oscillation in lambda over v, because that is just a distance over velocity. So we've reduced that down really quickly. That's why we have these transformations, is reduced it down that quickly into saying that's what the period is. Right, so that's that first bit. So then in B, what total vertical distance has the ship moved through during a time interval of P? So it's gone up to amplitude, back to equilibrium, down to amplitude, back to equilibrium. So it's moved through 4 amplitudes. So it's moved through 4A in order to do that, because it's gone up, down, up. And each one of those is an amplitude. Right, part C. Looks like the meat of the question here for 3 marks. Sketch curves for the ship's kinetic and potential energies as functions of time on the same plot from t is 0 to 2p. Right, okay, so say we were going to start, well, let's draw this out and put it as, let's just have positive energies. So let's go with this. So we'll make that p, we'll make that 2p. This is going to be our energy, that is going to be our time. So say then it had started in the middle, because we can start it wherever we want, because we don't know, the starting point obviously depends upon both x and t. So let's just assume it started at 0, 0, and we're just in the middle. So if we start in the middle, then let's think through what's happening in all of the oscillations here. So in one cycle, because we're just going to repeat again. So once we've done from 0 to p, we just do exactly the same thing again, going up to p, from p to 2p. So we don't really care about the next bit. We're just going to duplicate everything. So if we start in the middle, then we could say, well, let's put the kinetic energy and the potential energy. So if we're starting in the middle, Then we're going to go to the top. Then we're going to go to the middle. Then we're going to go, I'm going to have to scroll down again, down to the bottom. And then we're going to go back to the middle. So that's going to be our full cycle. So let's say we were putting minimum potential energy at the bottom. So we can say potential energy, let's put that as 0 rather than minimum. Let's say it's actually 0 at the bottom. And we can say we got an equivalent of 1 at the top, like relatively speaking, we go from 0 to 1 in potential energy. So because there's so much we don't know about this, we won't be able to directly compare the kinetic energy and the potential energies. You know, we don't know the mass, we don't know how quickly this thing is going up and down. It's going to vary a lot. If you've got a very slow wave, then you're not going to get that much kinetic energy, but you're still going through a big range in potential energy if it's got a high amplitude. So we don't really know which one's going to be larger here. And then in the middle, we're going to have a half here, we're going to have a half here, and we're going to have a half here. So this is what's happening with our potential energy. So we're starting somewhere in the middle. Then we're going to go up to some kind of maximum. Well, we're ending at the middle. We've also got a midpoint in between. We've got a maximum here and a minimum there. So that's what's happening with our potential energy. So, because remember on this, we're thinking is slightly different to what you might have seen with waves in the past, where when people have been talking about the potential energy and kinetic energy, it might be something to do with you're looking at a system like a mass on a spring, in which case you've got a constant amount of energy, which is an interplay between the potential energy of the spring and the kinetic energy of the mass that's on it. It's different here because we're just talking about the potential energy and the kinetic energy of the boat. We're not talking about anything that's going on with the water. You see, we're talking about the ship's kinetic energy and potential energy because that is changing so much. So it's not like having just something bobbing up and down on a spring or on a pendulum or something like that. So it's a different effect that we've got going on here. I suppose it's got similarities with a pendulum, hasn't it? But not the spring one. Right. So we've got that. So in the kinetic energy, when we're in the middle, we've got a maximum. And when we're at the top and the bottom, we've got 0. So we know we've got, because we're hitting stationary points at the top and the bottom. So we know here we've got 0, there we've got 0. And then in the middle points, we're going to have a maximum. So we got a max, we got a max, and we got a max there. So here we've got something changing much more quickly. So where we've got these, we're going to be going, I'll put it in red. Actually, let's duplicate, before I change color, let's duplicate this one round again. So we're going to have exactly the same thing going on for the next cycle for the potential energy. So we're going to have this happening. So at least that's got out of the way. Now I'll change over to red. So where we've got a top and a bottom position, we're going to have 0 kinetic energy. So we've got to go through there and there. And we're going to have a maximum every time we're hitting one of these midpoints. And it's open to debate as to whether that maximum will be greater than or less than the maximum of the potential energy. So I'm going to do it less than because I'm running out of space. So let's call all of those maximums there. And then we'll have another minimum there and another minimum there. So we join this up also in a sine wave, but it's a much tighter wave. So you could probably draw it better than that. Well, you could certainly draw that bit better than that. So yeah, it's looking something like this. So it's changing much more frequently than the potential energy wave. So yeah, so that's different to graphs you might have seen before, but I'm trying to think if that is going to be very similar to the mass on a pendulum graph that you're going to get for kinetic energy versus the potential energy. So yeah, you're going to get that. You might have seen that one before from that point of view, but don't get it mixed up with the oscillating spring ones, which are different to how this looks. So I think that is everything they actually wanted. I've gone on waffling on about this for a while. Sketch curves for the ship's kinetic and potential energies as functions of time on the same plot So the only thing we don't know, as I said, is we don't know which one's going to be higher. You know, maybe the red one would be higher. As in, if you've got something which is changing very quickly, you've got a very fast moving wave. You know, we got a high V value. If that's if we got a low, I suppose if you've got a short wavelength, then we've got high frequency. Or if you've got a high velocity. So if we've got either one of those, then it's going to push the red up. So red will increase with as V goes up or lambda goes down. So if you've got either one of those, then we're going to get an increase in red. So yeah, it depends. And of course, the amplitude as well is going to affect both of these things. So because the greater the amplitude, the greater change in the potential energy we're going to get, but also the greater distance you have to move through on each one of the oscillations. So that's also going to push the kinetic energy up. So that's that one. So that was question, whatever it was, question 24. So 2 to go. So on to question 25. Sketch that and that on the same axes, clearly showing the natures of the stationary points, labeling their coordinates. Write down an integral expression for the finite area enclosed between the two curves. Do not need to evaluate the integral, right? Well, that's a step up on previous papers where they've got us to do some really boring integrals. But there you go, we don't have to do that here. So we're going to have to simplify these things a little bit, haven't we? So we've got y equals, well, it's going to be x cubed, x minus 2. So that's going to be one of our curves. And the other one is going to be y equals x, 2 minus x is going to be the other one. All right. So how are we going to draw these? So let's start with the easy quadratic first. So that's going through 0 and 2, clearly showing the label on the same. So we just have to give the coordinates of the stationary points. So we've got a negative quadratic going through those. So we might as well mark that there. So that stationary point, which you can see a maximum at 1, 1. Right. So that is a maximum. So that's fine. Okay, so I've now filled up too much space on my graph probably to draw this in clearly. But this is also going to go through both of these points. So that's going through there and there. It's a positive quartic with a multiple root at x is 0. So we're going to be coming straight through this one. But we're going to get the usual touching point multiple root that we've got there. That's the only way we're going to be able to draw that one in. So we're going to have, what have we got? We've got a turning point here. So we've got a point of inflection at, so yeah, point of inflection at 0, 0. Then we've got this minimum kicking around. So we are going to have to differentiate for this because we're going to get stuck otherwise probably. So 4x cubed minus 6x squared equals 0. So we've got the x is 0 option. So we've already got that solution. We don't have to worry about losing it. So we can divide through by the x squared and say that 4x is equal to 6. X is equal to 3 over 2 at this minimum point. So we've got 3 over 2, which means that y is going to be something horrible. So y is going to be, what have we got on that? 81 over 16 minus 2 lots of that squared. So that's going to be, what am I doing? Minus 2 lots of that cubed. So 2 lots of 27 over 8. So that's 27 over 4. So that is going to be 108 minus, 108 over 16. So 108 minus 81 is 27 over 16, minus 27 over 16. So that is that stationary point. So that's given us that stationary point, point of inflection, that one, that one. So yeah, we've marked them all on then. That's 3 over 2 minus 27 over 16. So same axes, natures of stationary points, labelled in their coordinates. Okay, well, you can just write in again, pointing exactly at that one. Now we need to write down the integral expression of the finite area enclosed by the two curves. Okay, so the area is going to be the integral from 0 to 2. So we can do the top one comes out positive anyway, and then we could subtract the other one. So we got 2x minus x squared dx. Just check, double check. I'm pretty sure that's what it was. 2x minus x squared, yeah. And then we can take off the integral also from 0 to 2 of x to the 4 minus, what was it, 2x cubed. Yeah, looking at the reintegrating that differential up there. So yeah, it's just going to be that, which fortunately we don't have to bother to work out. So yeah, that wasn't that bad really, was it? That was quite a nice 7 marks. Again, pushing on to those questions towards the end of the paper can give you some pretty straightforward marks. Right, that brings us on to the final question, question 26, and it's a probability one. I was wondering if we were going to get probability turn up. We hadn't seen one yet. So 2 separate pairs of unbiased dice are rolled. We've got 2 8-sided dice and one of a 6 and a 10. Okay, so which pair is most likely to show a 16? Well, to get 16 on the 2 8-sided dice, we're going to have to roll, well, 2 8s, so that's going to be 1 in 8 plus 1 in 8. And to get a 16 on the 6-sided and the 10-sided, we're going to have to roll a 6 and a 10. Well, yeah, I should have said multiply there, not plus, obviously. So we've got 1 over 64 versus 1 over 60. So 1 over 60 is more likely. So we're more likely to get that on the 6-sided and the 10-sided combination than we are on the 2 8-sided dice. So that's a nice starter. Are any totals equally likely to be rolled using the 2 pairs of dice? Right, how do we... 1 mark. Right, so that should be quite straightforward then. So, well, we know that each one, we can see that for the 2 8-sided dice, we're going to get something over 64. And for the other 2, we're going to get something over 60. So can those things ever be equal to each other? So we'll be saying that 60m is equal to 64n. So that means 15m is equal to 16n. So are we going to get that then for... So we need a particular total, which is going to have the same... M and n have got to be integers. So we're saying then that it's going to, well, the lowest one you can get then is n is 15 and m is 16. So that is, that's a quarter of all of the outcomes being the same. There's just no way that's going to happen. So no, you're not going to get a quarter of all of the rolls being the same number for both of them. There's just no way. So we can say no on that. It's not even asking for an explanation. So that's quite an odd one. I mean, maybe there's a different way of thinking of it then. I don't know. Anyway, what is the smallest total that is more probable when using the pair consisting of 8-sided dice? Smallest total that's more probable when using those. Well, how do we think about this? Again, it's only 1 mark. So how are these things go? Well, nothing changes until you get... So what happens if you get the set? Well, even on 7, if you're going 7 as a total, we still don't have any real differences here because you can do 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, and we can do those on all dice. So the thing changes where, because that's just going to be 6 over 64 and 6 over 60. So it's still going to be more probable on the 6 and 10. So when we get to 8, we're going to get a change, aren't we? Because we're now going to get, if we got an 8, we're going to have 1, 7, and then 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 2, 1. That's what you can do on the 2 8-sided dice. But on the other ones, well, six-sided dice can only do those, so we'd have to have 7, 6, 5, 4, 3, 2 there. So we've got 6 over 60 for the six-sided and 10-sided, and 7 over 64. And 7 over 64 is greater than 6 over 60. So it's going to be 8. Right, this is a lot of work for not very many marks here. Which pair is more likely to give a total that is divisible by 3? Huh. 2 marks. How do we go about doing that? More likely to give a total that's divisible by 3. What could we do? We could think of, well, if we think of all the things. So the 2d8 roll is going to be, what can it produce? So if you've got a 1 on one of them, if we're going from 2 to 9, 3 to 10, 4 to 11, 5 to 12, all of these are going to be equally likely, aren't they? 6 to 13, 7 to 14, and then 8 to 15. Oh, we're going to have another one, aren't we? 9 to 16. So that's all what we can produce with the 2d8 options. So if we were then doing the other ones, the 1d6 plus 1d10. So I haven't actually explained what these mean, but yeah, if you don't play board games and role-playing games, you might not have come across these. That's just saying d8 is saying an 8-sided dice, so we're rolling 2 of them. So we got a 1d6, a 1 6-sided dice, and a 1 10-sided dice. So on here we'll have 2 to 11, 3 to 12, 4, 5, 6, 7 to 13, 14, 15, 16. So that's all of the permutations that we've got. I suppose we could just add up, just count up in there and say how many multiples of 3 we've got in each one of them. Seems a little bit unsatisfactory, but you're going to have here, you've got 3, 6, 9, 3, 6, 9, 12. Then it'd be 3 in that one, 3 in that one. This would have 4 in, and that would have 3 in. So we've got, what's that, 20. And then over here, you've got 3, 3, 2, 3, 3, 2, 3, 3. Which is then, how many 3s we got? 1, 2, 3, 4, 5, 6. So 18 plus 4, so 22. So we got 22 over 64 versus 20 over 60. So we've got a third there. And then here we've got more than a third, just about. There's an extra one thrown in there somewhere, so that is greater than a third. So there must be something on just how we're counting up there where I didn't need to do all of that. But so if you've got a quicker way of just getting the answer there, then let me know. But I mean, that's come out all right. It is going to be the 2d8 pair that is more likely to give that. E, given that at least one of the 8-sided dice has landed a 5, is a total of 11 or 10 more likely? So we've definitely got a 5. So we've either got 5, 6, 5, 5, or I suppose you could have 6, 5, because they're the only options we could have in order to get 11 or 12, with one of them at least being a 5. So we're more likely to get 11 than we are to get 10. So it is 11, well, for the reasons shown. You can show that picture for permutations shown. Okay, that was a bit of a sort of mishmashy sort of question, that one. It all felt a bit scrabbling around in the dark, trying to find answers to everything. It wasn't entirely satisfactory, particularly part D. So, as I say, if you've got a better option, then let me know in the comments. But that brings us to the end of PAT 2023. So that is up to date at the time of recording. So I can stop doing PAT videos for a while. I finally got through all of those. It's taken ages, going all the way from 2006, you know. So nice to have it done. And if you found it useful, then, you know, please throw out a few likes and subscribe and such like, because it certainly helps matters if you do.